Hey everybody, I see we got Kayla and Thacker here, and Lizzie, good to see you. Let's start with some 320 today. We didn't do any yesterday. So let's start with a little 320 and then do some 201. Looks like we're gonna do some confidence intervals. Hopefully my Pearson, I know Paige. It's like I've emailed the other instructors. I'm like, what are we gonna do? I'm just like, I can't believe it. My Pearson's started acting up weird Sunday night, and it's like, okay, it'll go back to normal. It'll go back to normal. But it's doing its my Pearson thing, which we don't like. Yay! Let's go. So decision trees, definitely check out Elizabeth. Let me think where I covered that in yesterday's video. If you're in our classes, you should, go to the link I sent out yesterday if you want to see some videos on that. We can do that a little bit later here, Elizabeth. Definitely know kind of what variables decision trees take, know how to read and analyze decision trees. And let's drop this in the chat really quickly right here. Probably what's really awesome, because we're gonna do a little 320 to start, and then we're going to go over back to 201. But if you haven't seen this playlist right here, I'm gonna drop this playlist in here. I'm gonna put the one for decision trees. Okay, good. I put decision trees on here. I was like, where's the decision trees one? So here is the speedruns playlist. And if you haven't seen this, check out the speedruns playlist. Good to see you, Alexander. Speedruns. So right here, check this out, Elizabeth, and we will come back and we will do this. So there's the speedruns playlist. Just practice up, Alexander. You got this. You got this. We're going to practice up today. That's what we got. Check out that link right there, Elizabeth, and we will come back and we will check it out. So, Elizabeth, stay tuned. Stay tuned. Let's see right here. I'm turning on my volumes. My first question is in relation to that question as well. Yes. So Thacker and Kayla were wondering, could we possibly go over evidence and visual backing for an explanation on part 5 of task 1 for assignment 8? So let me go grab that. I got all the versions of it open. So let me go grab that part of the assignment. I wrote it, but sometimes you just can't remember what you wrote. I think we're looking at an unusual row, right? So Kayla and Thacker remind me, I think we're looking at an unusual row. And the unusual row is going to be something that has very, very high leverage. We can kind of recreate this right here. Let's make a multiple model to start. So I'm going to use a totally different data set. And you guys can tell me if I'm wrong right here. I'm going to use the body fat data set. So it's important to know that this loads in data that is kind of preloaded into R. So when you use data, that's not how we load in Excel files. I might actually have us use an Excel file in an upcoming assignment, but this has us load in preloaded in data. You bet, Carly. We can do that here in a little bit. You got it. And we have, I don't think we've done the junk mail one yet, but let's do that here a little bit later. We got a lot of office hours to come. Stay tuned, everybody. Print the numeric rows for pairs. Exactly. So we're going to see a really great way of looking at this. Let's limit this data set, though, because it's really big. So this data set right here, the body fat data set, has a bunch of measurements, as you can see, for like we can measure people's body fat, their age, their height, their weight, all these things right here. And let's take a look. And hopefully my Pearson starts working properly. I've asked the other instructors what to do about it, and I'm hoping like we're probably going to make some decisions here about it, because I'm really sorry, everybody. I'm like, it'll start working. It'll only not work Monday morning. It'll only not work most of Monday. Oh gosh, it's not working into Tuesday. Like when I saw it wasn't working this morning, I just wanted to scream. I'm just like, are you kidding me? Like the day of the test and the day before the test, my Pearson decides, nah, it's just gonna not work. Just gonna have a bit of a problem. And it's like, oh my gosh, my Pearson, why you do that? So we're going to talk today, or Wednesday and Thursday, about what it means for something to have high influence. Look at that over there. Ignore that. Oh, has I already run it? Oh, that's influence. Ignore that flop behind me. Oh, cool. We got some, awesome. Wow, look at that. That's cool. Okay. So what does this mean? Okay. So these plots right here are going to be super important, and this one might have a high influence. So here's the important things for 320. This region over here is high leverage, and these regions outside of here are high influence. Now, what percent of points would you expect to be between 2 and -2 deleted studentized, kind of like standardized, kind of like z-scores, residuals? Between 2 and -2, what percent of residuals would you expect between 2 and -2? Stats 1, you can also answer this question. And let's throw out some points here. We haven't thrown out points today. So who's going to tell us for 100 points? What percent of points would you expect between 2 and -2? What percent of the observations would you expect between 2 and -2 standardized or studentized, which means it's a t-score, which we'll be talking about in 201. 95%, that's the empirical rule right there. So pretty much due to random chance, 95% of points would be contained within 2 and -2. So a studentized, when you look at this whole thing right here, deleted studentized residual, what a deleted studentized residual means, and I have to show you with this following plot. So what a deleted studentized residual means, plots, is if we go and we make a drawing like this right here. Here is the line right here. This is the line, and this is the line with the red point. So a deleted studentized residual, and I'm going to draw it on the screen right here. Let me... 2 seconds, class not over. So this is what is a deleted studentized residual. So let's talk about what a residual is. A residual is just how much the model misses by. But a deleted studentized residual, just think about the deleted part for a second. The deleted residual is going to be how far it is away from the line. This is a deleted residual, and E is residual, deleted residual, and this is just residual. Does this make sense here, Kayla, that a residual is how far a point is away from the line? I'm blocking right there if I appear. So the residual is how far a point is away from the line, but a deleted residual is how far the point is away when we delete it from the line without its influence. So when we say a deleted residual, it's how far away it is from the line after we move its influence. So you're going to get a bigger residual because it doesn't have its influence. So a residual is just how much we miss by, but a deleted residual is how much we miss by when we remove the point's influence. Does that make sense right there? Like this on the right is a residual, and then on the other side, I'm showing the deleted residual by removing the point's influence and finding the residual's distance to a line where the point is not part of the influence. We call it a deleted residual. So show me the influence plot. Oh my gosh. Oh, Connor knows what we're getting into right here. So what we have right here, look at this influence plot, Connor. Connor, do you think there's a point that is, or at least a single point? So the point is removed from the data set to create the new line? Exactly. Kayla, that's exactly it. This right here, this red line right here, actually it says width right there. Let me undo. Oh, we can't redo it. So let's look at this again right here. If we go boom, 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 and then I like to go undo and then I go this right here. Oh, sure. Yeah, so you can look at like here is the line without this red point, and you can see the deleted studentized residual would be off the scale. So this has a very small residual when it's in here, but if you looked at its deleted residual, well, here's the line without it, and it would be a humongous deleted residual. We can't even really measure it. So deleted residuals are always going to be bigger. This one's a little bit crazy right here. We'll try to make it. So there's a line and then this right here. So the deleted residual would be with only the black points. Does that make sense? Like here's the deleted residual. I'm showing you the deleted residual right now. Here's the residual because the residual is just how far it is away from the line. But the deleted residual is we remove the point and we would graph the distance to the point. Like this black line is without the red point's influence. So this is the distance for the deleted residual because we're not letting the line, yep. So that's the idea of a deleted residual right there. We remove the point and we get a line without it. And we'd say, how far is it from the without it? So this is the residual. This is the deleted residual. So deleted residuals are always going to be bigger. And then when you talk about the idea of studentized just means it's turned into a t-score. So we're doing it on the t-curve, like the idea of 68, 95, 99.7. Just think of this as standardized. Don't think too much into it. It just means it's a z-score, basically. It's technically a t-score, but t's are like z's, very similar. T's are just more exact in their calculations. And we don't have to worry so much about those calculations. We should understand, though, that we're putting the limits here at 2 and -2 because about 95% of these points would be expected to be between 2 and -2. So this is unusually low. This is unusually high. And the idea of leverage right here, I'm just going to briefly mention this and we'll go over it more in class, is how extreme points are on their X scale. So if you think about leverage, and Connor's right here. Connor's like, this distribution looks insane. Connor, do you want to see what makes this unusual? So this is what we were talking about. We're going to show some cool code right here, and I'm going to put this in the chat for anyone watching for 320. We're going to take this code we have right here, and we're going to use it in the pairs command. Connor, I might actually need your help for this. I should be able to do this. I've done it multiple times. The first time I ever did it, I actually had graduate students help me out. I mean, I'm talking like 6 years ago now. So here it is. It's that point right there. I can already tell you which one it is. It's this point right here that's super odd. And we could, here's the unusual points. Let me go here to unusual. You won't have to do this for yours, but I'm gonna make a vector of unusual just so I don't have to rewrite those every time. So these are the unusual rows right here. Does that make sense? Like I've made a vector of unusual rows. I think I could also just take that by saving, you can go to influence plot and go here to leverage. And so I could have done this right here, and that should also, it also plots it. Oops. Yeah. So, okay, we could have done that too. So Mr. T says, so now we have the unusual points captured. I think, Connor, do you see where the other one's at? I think there's one more. It's like right there. It's like right on the edge of it. It's just barely. Outliers are potential influential points. One deemed influential, we examine the amount of leverage. So what two things must, so Kayla, great review right here. What two things must a point have to be influential? They must have a large deleted studentized residual, and they must also have large what? So that's the other thing. You need two things to be influential. You need to be one far away from the model, which is unusual in the Y space, and we'll measure that via the deleted studentized residual. So this is the Y space, and then just think about the other axis right here, and that's the other unusual feature you'd have to have. Unusual feature number one is your unusual in the Y space, which is going to be your deleted studentized residual, which we just talked about, and then the other unusual extreme in the X space. I know, Paige, I'm so sorry, Paige, I'm so sorry. Like, hopefully it's going to be working, and I've sent out a distress email to the other instructors, and I'm hoping we come up with a nice solution of sorts or something, but I've said, hey, we should figure out something to do about this. And the least I'm going to be doing is extending stuff. The least I'll be doing is extending. Like that's, I know right now I'm going to be extending assignments. So good news is I'm extending assignments. Second, I'm hoping we say something more than that. So I don't want us to come forward as a team. So I'm so sorry, Paige. And we'll be doing 201 here in about 17 minutes. Let's do it. Noon, 201. So unusual in the X space, unusual in the leverage, so Kayla and Connor right there saying the same thing. We are going to have right here, unusual in the X space is unusual in the leverage right here. So unusual leverage is unusual in the X space. So we have here 3 points. We have here this point, which is barely unusual. This point, which is, I know it doesn't look like it's super unusual, but it's only dwarfed by like this mega sun right here. I'm so sorry, Lizzie. We're going to hope everything gets back to normal, and we're going to do some studying here in 15 minutes. So we have right here these 3 points, point 1, point 2, point 3. And let's take a look. So we have the pairs command, and I can probably tell you that this point right here is probably this one right here, because that's super unusual in the X space. When you look at the X space for it, like just weight, like if you look at across weight across here, it's far away from the model. That would just be a model predicting body fat from weight. That'd be its deleted studentized residual, or basically residual, but also it's just extreme in the X space. So it has to be this point with that much leverage. Like that's gonna be the point. So what we're gonna do is we're gonna write a really cool code right here. We're gonna go outside the pairs command, and we're gonna type PCH, and let's type 2. Good, that's what we want. So we're gonna do PCH equals if else row dot names are row names. There we go. Row names. Okay, of body fat. Row names of body fat contained in unusual. And let's see if this runs. Gotta make sure I have all my parentheses right. Good, that did it. That ran, got it. Okay, good. If they are contained in Then we want to use 2, if not 10. We'll see how that looks. Did this work? It looks like it ran. And we fixed our code now. We've got it working. So now it's going to do a triangle. I don't really mind what else the dots look like, but let's change it here a little bit. Let's go 8. You know, let's switch. Let's do that. Let's keep it like that. You can play around with this right here, whichever one you want. But now that we wrote this command right here with this if else, we're going to take this if else and we're just going to do another line and we're going to do CEX. And so CEX is character expansion. And a student taught me that about a year ago. I was like, I do not know what CEX stands for. And they said it's character expansion. And I said, oh, thank you very much. Now I know what CEX stands for. Look at that. Now we've got the triangle a lot bigger. We're going to do one more thing right here. We're going to go col, which stands for color. And we're going to go here and go red. And there we go, red on that. And we're just going to go black on this. And I think that's done it. There we go. So we can see the 3 unusual points pretty clearly right here. And you can see how extreme they are away from the model. We don't really see much leverage there. It looks like the weight is extreme leverage. The height is extreme leverage. I know. I was like, I don't know what CEX stands for. And they're like, and they looked at it, character expansion. So thank you, Connor, right there. Yep. It was Connor who told me that. And PCH, what does PCH stand for? I know point style, it's point style, but I can't remember. But CEX is character expansion, which is the size of the character. And Connor Moore definitely told me that right there. I remember what room we were in, and I always say my students teach me things and help me remember things. So thank you, Connor. But this code right here, especially, I just like the way it looks, and I like the output it makes. So we're going to drop this in the chat. Pacific Coastal. I did not know that, Alexander. Alexander, I had no idea on that. Plot character. Wow, there we go. That makes perfect sense. So Kayla, right there in the chat, is this code right here that you can use. I would also go, and I would take my unusual points. And so I could go here to body fat and take my unusual. I'm just going to put this in the row space. And here's the unusual. And I guess I only did the first few things of it. I think I only did columns 1 through 5 or so. So I think, right, age, weight, height, neck. Age, weight, height, neck, yeah. So if you look at these individuals right here, you can talk about how they're unusual. I know I lived in Cali for a bit. Does this make sense here, Kayla, on what I'm doing and how I've created a plot to kind of show what's unusual right here? And it's really clear with this point. We could also isolate this point. We can figure out which one it is. It definitely looks to be, if you look at the weight, it's 0.39. So if you really wanted to talk about just one individual point right here, you could just talk about that one point, which you guys are going to have more 1 point. Did I not just save the unusuals? Oh, I did. Good. It is. Now it's just showing the 1 point right here and what makes that 1 point unusual. So you can see like the extreme nature of this right here, and you can change it, make it any sort of thing you want. We could make the PCH way larger. That'll really make it, or the CEX way larger. This is the character expansion right here. So we're just going to double it. And you'll now notice it's going to double in size right there, making it a huge thing. Fantastic. Yeah. Do we have time for a second one? Yeah, let's take a look. So extrapolation check. When we look at the extrapolation check of something right here, so extrapolation check is going to tell us if something is unusual. And let's look at the extrapolation check. What extrapolation check takes, and we got it. Let's, yeah, because we'll start around. So extrapolation check right here. We've got the new data we're going to work with. Here's our model. This will run an extrapolation check on the data in the model. I think it's only taking the X variables within the model. Yep. Awesome. So to run an extrapolation check, and we could see if something is unusual, it needs to be an unusual combination of the X's. So an extrapolation is not just on one X. We can go here to new data, and we need to make a new data frame. So it's just like the predict where you have to put in the data. We're going to need these variables right here, so I'm just going to grab them for the moment. I'm just going to do one variable so I don't have to worry about doing a whole bunch of vectors. So we're just putting in these values right here. Age equals, let's do Brian. So Brian is 39 years old. Would Brian be an extrapolation in this model? Oh, I should have, well, I don't know. I don't want people to have to put in their, I don't want people like, put in all, I don't know my neck measurement. What is I don't know. 28. What is a normal neck measurement? Oh, I have a tiny neck. Let's go 37. I'm going to go towards the middle of that. Would Brian be an extrapolation? So would Brian be an extrapolation? So we should be able to type new data right here. It should work. There we go. I am not an extrapolation. So the way extrapolation works is the more towards you're the center, the more you are towards the center of the data. So if you have a model, like let's just look at the simple linear form. In a simple linear model, here's the model right here. The more you are towards right here, you would be at the 0 percentile. But as you go further out on the x-axis of the model, or the x's, and when the multiple form, you would reach towards the 100th percentile. So like in terms of extrapolation. So at the very center of the model, you would be at the 0th percentile in terms of like, here you are not extrapolating at all. Here you start to, you're not really extrapolating much. And as you get towards the end of the model right here, I guess we could go towards orange, and then you're going to be really extrapolating outside of this bounds. Like this is where you are truly extrapolating. So the idea of kind of this like further and further away, where's the binary classifier for... So with this right here, does this help make sense of kind of what the idea of when we talk about extrapolation, and if you think about it in the multivariate sense, this is where it might get a little bit confusing. And we'll see this graphic on Wednesday and Thursday's class. On Wednesdays and Thursdays class, we'll have a graphic like this where we have x1 here and x2. Now, what's confusing about this is we're talking about, you know, two x variables. And if we have a cloud of data right here, then extrapolation works the following way with this cloud of data. The cloud of data would have the lowest bit of extrapolation right here towards the mean of the x's. And then we would get to a little bit of extrapolation right in here. Not saying we are extrapolating, but I mean, you're kind of in the neighborhood of the 40th through 60th percentile right in here. It's looking like an egg. And then as you go further out, you're going to start, I guess this is, you know, like where you're really hitting into the iffy points of the model gets a little bit bendy, especially in its predictions. And then when you leave that area of the data, I guess we've already done, we'll go more extreme right here. Now you're definitely in the extrapolation zone in these combinations of the x's. Like these combinations of the x's, you do not have anything to narrow down your model on. And that's definitely extrapolation of the model. But then if you go even further out, you just hit open water. You're in the like, I don't even know what you're doing point of the model. Like the model is completely unreliable at this point. And the big thing to note about this is we're talking about the multivariate combination of x's. So you've got here, your model's really nailed down there because that's the mean of the x's. And this is a combination. This is not x and y anymore. It's the multivariate combination of x's. Your model's nailed down there. Your model has a little bit of uncertainty. Your model is getting a lot of uncertainty. You're outside the bounds of your model, so you're extrapolating, and then you reach very strong extrapolation. You're in deep water now. Does that help with the idea of what extrapolation is, especially in the multivariate sense? It's, do you have an unusual combination of x's? And with this code right here, we've identified that this 61st percentile means we're probably somewhere in here. Like Brian's not the mean of the x's. He's not like the most typical like person in this model, but he's not too far out from this model. Like this model's like, yeah, sure. He's, you know, about 60% outside, like towards the edges of the mean. You don't want to be on the 100th percentile. If you're on the 100th percentile, you've left the model. You're somewhere outside the x space in an unusual combination of the x's. If you get 0th percentile, then that means you are the mean of the x's. So, and we could confirm this. We should be able to confirm this if we go right here to summary of body fat. And here's the summary. So let's try to confirm that the 0th percentile, if we go here and grab the mean, that's 18.938. Weight, oh wait, that's body fat. Age, mean age is 44.88. 5, and then mean weight. Oh, I see, it was kind of close to that. 9.2. Mean height is 70.149, and mean neck is 37 point. I was kind of close on that. I mean, I purposely gave that one. So now if you look right there, we have confirmed that if you look at this code and what it confirms, the percentile right here is the 0th percentile, which means we're at the center of the cloud of the data. So by doing the mean of all the observations, we've landed right here at the center. We've landed right there at the center of the mean of the x's. From assignment, finally choose one of your x variables and explain why you'd be extrapolating with your model. I didn't plan for people to use extrapolation check, but I think maybe you should. I don't know, that should be like a bonus or something. But we did put the 5-point bonus if you turn it in before Sunday. Finally, choose one of your x's and explain when you'd be extrapolating. Yeah. So when would we be extrapolating for one of these x's right here? And the answer is with this right here. Let me only do the first 5 rows. So this code right here, Kayla, will answer the question, when are we extrapolating? And technically, we don't need the y. Extrapolation has nothing to do with the y. So can you tell from this code right here when we would be extrapolating? Because extrapolation has nothing to do with the y variable. It's only going outside of the x variables. We always say in Stat 201, extrapolating. So when would we be extrapolating? Like, when do you start to see extrapolation? Like in the multivariate world, it depends on the multivariate combination of your x's. But when on some of these would you be extrapolating? And this has all the answers right here. So this is the answer to when would you be extrapolating. I should have put show numeric backing, but this answers the question right here. You are correct. Alexander just got another 50 points. Thank you, Alexander. You're exactly right. Outside the bounds of the mins and the max is when we're extrapolating. If you notice, there's a lot of Stat 201 and 320 like overlapping concepts. So your 201, 320 knowledge join in outside the min and the max. So if you're outside of the bounds of here or outside the bounds of here, and in the multivariate world, it's hard to think about like what is a multivariate combination. That's why we look at like the percentile right here, where previously, if we made predictions with Brian is in this percentile outside a multivariate space. Kayla, I'm sure you know, like I say I'm sure, but I'm pretty sure you know eigenvectors and eigenvalues. So if we were to make an orthogonal space, I'm going a little high tech, I'm going a little, I might say something wrong here, but if we were to make an orthogonal space of this data set, in terms of like the dimensionality and the this would be a 4-dimensional orthogonal space, would it? Phone's going crazy. I am getting so many random calls from fake numbers with fake names. And I think this one may answer. I hate that. If we were, yeah, I know who doesn't know eigenvectors and eigenvalues and eigen everything? So it deals, if you want to go more in depth in that concept and look into it a little bit more, but it deals with knowing how far we are outside of the space. When you think of in terms of like a orthogonal cloud of data. So it would deal with a 4-dimensional orthogonal space. How much have we left the space? And that's what that 61% is talking about. Like, are we outside of that whole cloud of data? You got it, Campbell. And does that help out, Kayla? Does that make sense we've covered how to do the influence plots and the extrapolation check, hopefully, and I'll let 320 finish up, and then Campbell, you got it. We're going to start doing some 201. Everyone, thank you for the positivity. It's been a crazy morning with my Pearson going crazy. Oh man, my Pearson, why you do this to us on the morning of the exam? Give me a heart attack, my Pearson. I half joke and then I'm not joking because my Pearson breaking is not fun. So we will, like I said, I've emailed the instructors. I'll take a quick peek. I'll see if they've emailed back. Let me see right here. I have not heard back from them yet. So I'm hoping I hear back from them soon. Let's see. Okay, good. Making sure someone has their test assigned for the current time. So that's the biggest thing, making sure everyone has their tests assigned, all that good stuff. Just replying everything as fast as I can, making sure everything's working. You gotta like something starts to fall apart. You're like, no, we got this. Don't fall apart. You're not gonna break my Pearson. I will hold my Pearson on my back and carry it forward. I can't do that. I cannot control my Pearson. So that's the hardest thing is when, you see, look, it says on their website, what's it say? Technical teams have confirmed an issue that may impact your, wow, that's great. Thank you for saying that, my Pearson. Yeah, your technical team has confirmed an issue that may be impacting your math, business, English. Yeah, you may experience difficulties with signing in. Some customers are experiencing. That's awesome. That's great. Yay. Thank you, my Pearson. Thank you, my Pearson. My Pearson, why? Why you do this, my Pearson? Okay. Oh, let's continue on. Okay. So let's see right here. It looks like I am signed in. Sometimes when I go over, it works and then it doesn't work. Like sometimes it's working and then sometimes it's not working, which is just tough. It's just tough. So I agree, Paige. And it looks like I'm clicking the assignment manager right now and it's just saying no to me. It's just like, nope. You want to see the assignments? Not today, man. Not today. So we might cover some topics. What do people want to cover? Yeah, oh definitely. Lizzie. I'll probably even like move it back to Tuesday because we're gonna wait till my Pearson gets back to normal, and the least I can do is move the assignments back. I've emailed the instructors about this. There's just one assignment this impacts. I mean, that's not good. It's not a good thing, but really, what's that, Alexander? Lighten the mood, Alexander. And feel free to ask a question because I don't know if we can do questions 7 on practice exam. You got it, Campbell, because I don't know if we can do my Pearson right now. I would do my Pearson questions. If anyone has a screenshot of one, you can send it to me via the Discord. Like if you are currently working on one and you want me to work on it, message me on the Discord or say, hey, Brian, I sent you an email. If you have one for me to do. And I think we did do the philanthropic email one. Actually, I can do that one by memory. So someone mentioned wanting to do the philanthropic email question. I'm pulling up the exam review material. So I do know the philanthropic email. It's a confidence interval question. I can do the philanthropic email by memory. Do you want me to go over the t-distribution counter here in a moment? So I should just let it go for now. And yeah, I would focus on studying, especially if you're in my section. You will get more time for it. I can't imagine the other sections not giving you more time. I'm loading up the practice exam right now as we talk. But I'm 100% give everyone more time, like 100%. You will definitely get more time. So do not worry in my section. You are getting more time for this. Cool. Number 7 is a simulation question. I am taking number 7 off the practice exam here. Okay. So do not worry in my section. I should say that via email too. Is this the one that people want right here? So everyone, if you could, would you find the truth, or would you dare to do anything without any restrictions? I like truth. I like knowledge. I'm gonna take truth right there, Alexander. Yay, thank you so much. I really felt good about the probability, and now that I'm doing it, I feel not so good. Oh no, we got this. Is this the one right here you're talking about? A grocery store thing wants to do a giveaway. Let 0 and 1 represent gift card winners. 2 through 9 represent people who did not win. So we need to go through here and mark these questions right here with who won. So let's go right here and mark everyone who's winning. And tell me it's 0 and 1, right? I'm totally going to miss one. So what I'm doing is I'm marking the winners. Someone won if they got a 0 or a 1. Based on how these numbers were coded. This is where I think usually the mistake happens. Based on how these numbers were coded, what is the probability of winning? We had right here, the way they were coded is 0 and 1 are winners, and 2 through 9 are losers. So these are winners, and these are losers. So based on how these numbers are coded, what is the probability of winning? Based on how these numbers are coded, what's the probability of winning? Now, this is not from the simulation above. This is based on how these numbers are coded. Oh, Campbell, that's what happened? Yeah. So based on how these numbers are coded right here, what's the probability of winning? 20%, exactly. So this is based on how they're coded, because there are 2 numbers here and then there are 8 numbers there. So 2 out of the 10 numbers. So 0 through 9. A lot of times I think 0 through 9 is confusing, but 0 through 9 is just like 1 through 10, but we're doing it with single-digit numbers. So 0 through 9 is just single-digit numbers. And just think about the 0 going over to the other side and being the 10 right there. So like 1 through 9, or 1 through 9, then you put the 0 on the other side and you get 10. It just allows us to do one-digit combinations. In the simulation above, what is the probability that we get exactly 2 out of 5 winners? So exactly 2 out of 5 winners. I'm going to put some check marks here. So 2 out of 5, 2 out of 5, 2 out of 5, 2 out of 5, 2 out of 5. Do a double check. I'm trying to see if I missed anything, but I think we've done it. So that's 5 times. Please correct me if I'm wrong. Great questions, Campbell. Yep. Do you see there's 5 and I think 20 rows? So we have 5 over 20. Satisfy it. And that's 25% via the simulation. And so in this simulation, we see 25% because 5 over 20. So what needs to be done to improve this estimate? So what law would say if we do more trials, we would see the probability in the long run starts to approach the truth? So if we were to say we do more trials, we would start to see it approach the truth, which is the answer. Good to see you, Connor. So if we do more trials, like if you increase the number, and that's the answer to the question. If we do more trials and we do repeated trials and we extend out, like we just continue to do more trials, like you increase the sample size here, do more trials of the simulation, what law of very large amounts of trials says that if you increase the amount of trials you have in simulations or in observing something in reality, you are going to see in the long run the true probability of an event. So that graphic, law of large numbers, great job, Lizzie. Yep, law of large numbers, exactly. So that's what we're saying down here is increased trials. So the law of large numbers states, and increased trials is the same sort of idea, that in the long run, if you increase the amount of trials, you will start to see the true probability. Like it might start out like way off. It'll bounce around a lot of times. Like it'll start off and then it'll start to like go in and start to narrow down in. I think I have in here. Let me try to find it real quick. I have a simulator I made. Oh, we just lost Connor, and then yep, Connor, if you're still here, I made a coin flip simulator this semester to show the law of large numbers, and so I coded this right here, and it should bring it up. This should be a ggplot with the law of large numbers. Yep. And you see it started out 100% heads, and then it went down, and eventually it starts to go towards the truth. And so I can do another coin flip here, and I have it actually set to do 100% heads. Oh, look, see, and then it goes off, but it'll always go towards 50% because it's a fair coin, at least via this simulation. So you can see right here, and wow, look at that. It went like heads and a bunch of tails. It had a ton of tails at the start. Whoa. So did I call this flips or something? Where's my graph? So I'm actually very interested. Data. Flip. So there's the flips. And let's look at head of data. Because it started off. Oh. Is that not how I started? Oh. And there's the percent heads. Yeah, so if we go to percent heads. So anyways, another question. Yeah, it started off heads, heads, tails, 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 tails. It started to go tails a lot because it started to go, yeah. If you can see each time it goes down, it's getting tails. And then on the 9th, it actually, or the 10th, it went back up a little bit. But it starts to zero back in. And that's the law of large numbers right here, that since this is a fair coin in the long run, but look at how it bounces around. And that is like our example right here, that we're going to see in the long run with more trials the true probability of observing 2 winners. So if we increase the trials, which we are literally doing right here, here's the idea of increasing the trials and in the long run, because you might not see it in the short run, like especially in the short run. Get so many fake emails or something. Look at that. Ah, it's so cool. I just love it. What question do people want to do? Just look at this one. It's like, so what question do people want to do next? What question? I wish Connor was here. I'd tell him about the story about making this, because I had an issue. So I cheated with this. I was like, whatever, it's a simulation. It'll eventually level off. I had an issue with it registering the percent of heads because yeah, I was taking from the table the percent of heads, and I was like, okay, I'm gonna make it work. I had a question about my Pearson not loading. Yeah, man, we will definitely be extending the assignments. That is a given. My Pearson is loading like super slow, and is there a question people wanted to do on my Pearson? So my Pearson's loading super duper slow. We will be extending it, and I've emailed the other instructors to say like, what else should we be doing? Like, we try to have a conversation as instructors. I mean, I can move assignments. Like that's something that is within my like. Brian can move assignments. Like you can. We're all instructors. If we go to a different pace, that's just kind of like course to course differences. And so I had it due tonight. I think it's fair if we move it. Oh yeah, you're one of mine, Alexander, right? I think you're in the asynchronous. Yeah. Everyone, all my students. If you're one of my students, it is extended from tonight. Yeah, let's go ahead and do that now. Let's go ahead and do that now. Okay, so I'm right now. This is gonna well, I can get it done for one class right now. Like even me extending this, I clicked the button right now and very little's happening. So I clicked the button to extend. I clicked change date and assign status, and it's not yet pulled up the window for me to do that. So even changing the date and assignment status. Question 6. Yeah. Is that on the practice test, Campbell, right there? We can do that. Any fixes or alternatives? Just trying to hopefully, I just need an explanation on part 6 of question 6. Yeah, let's go take a look at that. Part 6, question 6. This is the always hot water heater one. So we're just hoping it starts to work again, and kind of, I emailed like, what is a good way to us to be fair with this and help out, and I'm just gonna hope it starts working. Yesterday I was like, okay, it's gonna have a problem for a little bit of the day, and because they've had problems before and it usually fixes. Like I've had people email me, and by the time I reply within an hour or so, it's fixed. But not today. Not today. Today's not one of those days, or yesterday and today is not one of those days where it's like, give it a moment and it'll fix. Because sometimes it has like a 5-minute hiccup, but that's not today. So what is the most important thing? And do come to today's class. We're definitely doing some big review today's class. So like I thought about like, what are people missing? What are people not understanding? And I looked over like old tests to see kind of where people might get stuck. So today's class is gonna be really huge. Please come to today's class. One of the big things that I always ask people to do whenever you get a problem is to mark the notation. So if we see right here, I've done this problem a few times, so I'm able to identify the notation. We have right here, they are going to install 50 always hot water heaters. Not today. Why do you do this to us? So this is going to be their sample size. Always try to like mark these and figure out what they are, because the next one's a little bit confusing. They know. So they know right here, let's say this is the truth, that this is the amount that go bad after 10 years. Or I think that's the amount that last. So that will last 10 years. Yep. So the amount that will last 10 years, the amount of always hot water heaters that will last 10 years is 0.25. So what does that make that in notation? In notation, that 0.25 is what? Exactly, Campbell. Yep. This right here is P. Now, what I would do is if I had this information, I would automatically go through and start solving for things like, we'll just go over here. I'd go mu P hat is equal to P. I'd go SD P hat is equal to P times Q over N square root. And use your formula sheet for this. Use your formula sheets, which we reviewed yesterday during office hours. So use your formula sheet. And let's go here, mu P hat. Well, I mean, if it's P hat, well, then that's that. So we're just going to put here 0.25 for this, because that's what P is, mu P hat, and that's what P is. So now we go P times Q over N square root. And there we go. About 6%. So about 6%. 0.061. So, hey, Brian, can you help me with understanding, the input part 5 on task 1? Which one is that? Roderick, explain again, and then we'll do it next here. We might have done it at the start. Interpret part 5 on task 1. Which one is that? Explain again. In this example, the sampling distribution of the sample proportion is what would happen if we take a sample of 50. So if we take a sample of 50 always hot water heaters, this is what we might see in a sample of 50. So we're talking about with this distribution, what might occur in a sample of 50. And the most likely thing is that 25% of them will last that long. So that is the amount we would expect. Now, one thing I do want to say, and make sure this is very clear, that these conditions right here of random, 10%, and success failure are the same conditions we have for confidence intervals. So take a note on that. These conditions right here of random, we randomly select these water heaters, and 10%, these water heaters are less than 10% of all water heaters. So what if this company were to only make 400 water heaters and we're taking a sample size of 50? So like we say, we want to see if this sample size right here meets the 10% condition. Yes. Check out the start of the video, Roderick. Rewind the video, and you'll see we do some really great graphics, and it's in the chat. So check out the start of the video. The first 20, 30 minutes of the video, we go through and I do the high leverage influence and show the plots for it and show the numeric backing. So check that out right there. So because Kayla was here when we did that part, so check that out. If you don't see it, let me know. But it's just, you can rewind. Yeah, tell me if you don't see it. So with this right here, we see that this would not meet the 10% condition. Does everyone notice this? That right here, if you have 50 taken from 400, like if we say 400 are made during a given day and we take 50, we would sample more than 10%. So in this problem right here, you have to assume that they are making more than 500 always hot water heaters to meet the less than 10% condition. So it's very key that we ask, is this less than 10% of what we are making? And if we make more than 500, we meet it. If we make less than 500, we don't meet it. The success failure condition is the last condition. And I do want to make it abundantly clear that these three conditions are the same conditions for confidence intervals. These are the same three conditions right here. This one's done a little bit differently. It's the same though. It's the same condition. I want to make that abundantly clear, like hint, hint, hint. So the random, we randomly sample less than 10%, and we have success failure, which means we need to have at least 10 successes, at least 10 failures. And also with this right here, this is only for categorical. Success failure is for categorical data, and we're dealing with proportions right here. So that's when we use success failure. So when we do this right here, we have 50 always hot water heaters. So we have N equals to 50 and P equals to 0.25, Q equals to 0.75, and oops, wrong button. And then we have, so we need to do NP and Q. So 50 times 0.25 equals to 12.5. And then we have here the other side of it, 50 times vanish, boop, and 0.75 equals to 37.5. And so this is NP, needs to be greater than or equal to 10. We satisfy that. And this is NQ, which is the other side of it, needs to be greater than or equal to 10. We meet all those conditions. We're almost down to the last few parts right here. Let's take a look. So regardless, calculate the mean and the standard deviation. We calculated this earlier. So do remember, we calculated this earlier up top. We have this is equal to mu p hat is equal to p. And that is just what p is. So p is equal to 0.25. That's the mean of the distribution. The second one is going to be the standard deviation of p hat is equal to p times q over n square root. And we calculated this earlier. That was equal to 0.061. Remember that P and Q. Sorry, it's a longer one. Sorry. I figure sometimes people watch these and they don't know these other parts. That's why I'm like going as quickly as I can to the final parts. If you meet all the conditions, we will have a normally distributed data. Suppose that after 10 years, she finds that 16. So Campbell, here's the practice we need. You ready? This 16 out of 50, what's the notation here? We're almost to the last part. Because I think you said, I'm trying to see where your question was. Part number 6. So we're almost to that right here. So this is the parts that are going to matter right here. So 16 out of 50, what's the notation on this? 16 out of 50. With 16 out of 50, what's the notation for 16 out of 50? Because now they find that 16 out of 50 did not last. So 16 out of 50 is going to be what in notation? So 16 is going to be x, and 50 is going to be n, and we would get here x over n equals p hat. And so, yep, great job, Lizzie, right there. This is going to be p hat, so that is 32%. And because 16 over 50. And that is p hat. Using your answers, calculate the z-score. So the z-score is going to be p hat minus p over p times q over n square root. And now we're just going to plug in the numbers we have, 0.32 minus 0.25 over 0.061. And hopefully we can see that that's going to be a little over 1 standard deviation right now. So this is the p hat we just calculated. This is the mean of the distribution, the 0.25. There it is right there. That is the mean. And the standard deviation is 0.061. We calculated it right here. So p hat minus p over that and 1.14. And we get here to the last part of the question. Great job, Campbell. So given your answer in part 5, would you consider 16 or more hot brand water heaters after 10 years unusual? So would this be unusual? And it was wrong on the last decimal. Does that matter on the exam? It shouldn't. Let me know if when you look at your answers, like, let me know if for some reason when you look over what you get right or wrong, if you're off by like a single decimal, because I'm usually like, yeah, whatever. Like I'll give points back. We also have margins of errors, but look over what you get wrong. If you're like, hey, Brian, this answer said 1.13 and I got it wrong because I put 1.14, let me know and I give points back. Like if you put, like if it doesn't accept it, so just let me know. Great question there, Campbell. And so is this unusual or not unusual? And so if we were to draw this right here, good to see you, John. If we were to draw this out right here, it would look the following way. It would be about, if we draw this out, it's going to be about right here. And so is that unusual? You should be all right. Yeah. Like we're pretty nice on the rounding, and questions usually say round to 2 decimals. Always carry all your decimals till the end, though. That's a good practice with mathematics, is like don't round numbers until your final thing. Like when it says round to 2 decimals, don't round along the way because you'll lose points. Like you'll lose like stuff. Good to see you here, Sam. So is this unusual right here? We've got the z-score for it. Is this unusual, yes or no? And why would it not be unusual? Because that's the answer. Is this unusual, yes or no? Because we're going to take and plot it as a z-score down here. So is that unusual right there? Is a z-score of 1.14 unusual? So it's within 2 and -2. So since it's within 2 and -2, it's definitely not unusual. And you'd be fine. I see there the 1.148 and the 1.413. Yeah, you'd be fine. We hopefully, and yep, not unusual because it's within 2 and -2. Usually, and I like to say outside of 2 and -2 is where things start to become kind of unusual. This is your kind of unusual range right here. It's definitely very unusual outside here. So this is extreme. Like these are extreme outliers. So this is very unusual. And outside of 2 is kind of unusual. Like sort of. Like, yeah, it's sort of high. Like that's kind of high. Sort of high, kind of high. So it's measures of degrees. Nothing becomes unusual after a certain point. It just becomes more and more unusual. Can you do number 12, part 4? You bet. Let's do that right here. Great questions. Aaron, good to see you here. So let's keep working away, doing more questions. We're going to pull up another question right here. So was it question number 12? Is it the decision tree? Cool. We got to grab the decision tree right here. Let's grab the decision tree. And here we go. There's the decision tree. Let me take the rest of it right here. Here's the decision tree output, leaf report, and all this good stuff. There's that. And then we need the questions. There we go. Let's do all the questions right here and see how we do. Okay, there we go. So the first thing we need to do whenever you get output like this is start associating what is in the output. Oh no, Campbell, no worries. I'm sure that helped out people. We had Lizzie working along with us and everyone. Campbell, thank you so much. That's our goal, is to just do as many questions as we can. And that was a really great question. Like, don't worry. Like, that's, and I'm sorry to anybody if I I didn't redo a 320 question. Well, because we're just trying to do as much as we can, as best as we can, and as clearly as we can. And so I thank you for being here and practicing. It just helps with, practice to be here. Okay, let's do this. Next question. So the first thing I'm going to do, I know I keep going up and down, is I'm going to go to my tree. I'm going to make sure I know that this is leaf 1, this is leaf 2, leaf 3, and this is leaf 4. And notice I'm just going to where the dividers are at between the leaves to talk about the different leaves we're working with. Going down here at the bottom, we can see this is leaf 1, leaf 2, leaf 3, leaf 4, and if we had printed tests, I'd print off some tests and I would have everyone practice this. I probably wouldn't bring it for everybody. I'd be like, hey, you need to write on this right here, leaf 1, leaf 2, leaf 3, leaf 4. And also we go down here to this output and we do the same thing. We put 1, 2, 3, 4. And one thing we should know immediately is that let's look what the smallest leaf is. You can see right here, leaf 4 only has 16 people in it. There's the 16 people. We see 1, 2, 3 people with a mix of views. And look down here. 3 people with a mix of views in leaf 4. So it's important to note that what you're seeing here in leaf 4, this is leaf 4 right here with 3 people in it, with a mix of views. There's the 3 people with a mix of views, and you can see the 3 dots literally right here, 1, 2, 3, and they're in leaf 4. And here they are right here. Out of the 16 people, there's the 3 people. And you can see down here in leaf 4, those are the 3 people. One thing I also want to point out that this is the distribution of the y variable right here. So when you're looking at this is the y variable distribution, and these are the x's over here. So those are the x variables right there. So now that we know how to read this, let's start looking at the questions. The questions have the following. How many more liberal students are represented report going to church at least once a month? So let's go up here, and we have go to church at least once a month. And these are the students who go to church at least once a month, and they are part of people in leaf what and what. So these people are in leafs what and what. I'm starting with the random chapter. Do you have any suggestions? We got some good practice problems on it. I do some during the speed run. Do I have the speed run still in here? Check out the speed run if you haven't. I don't have it copy pasted here anymore. I've got some speed runs going over it. Just the more of them you practice. So the speed run has some quick versions of it. And you are correct, Campbell. So Molly, this can help some, but practice that right there. Good to see you, Deanna. And so you are right, leaves 3 and 4, if you join these back up, these would go back up into here, you'd go, and they'd go back up into here. So we want to know the students who are more liberal, and that is going to be the students in leaves 3 and 4, who go to church at least once a month. There's the yes on that. And we want to know the students who are more liberal. So what would be the answer here? What amount? Is it amount or percent? So watch out. If it's amount, you're welcome, Molly. Hopefully that helps. It's some quick versions of them, but just, keep asking questions. We could do one after this if you want. And we also did the simulation one here also. So always follow the rules of the simulation. This one says how many. The answer to this question is going to be 29. I got that from adding together these two numbers right here. The more liberal students are these, and they're in this leaf. Notice how this is leaf 3 and 4 right here. Great job. Yep. And so that is going to be these more liberal students right here. And it'd be very hard to add these up, but they add up into this. I wouldn't be able to add them up from this output, but I know they're in leaves 3 and 4. And if you add them back together, they would go into that right there. The people who go to church at least once a month. And that's what we see down here in this output. It's the same output, just kind of easier to read. And that says 20 and 9 right there. Now, if it said what percent, maybe, if it said what percent, we'd have to take 29 divided over 317. So we could get the percentage right here for this leaf by doing the following. Very good question right here. 29 over 317, and it's about 9.14%, or you could do it as a decimal. So that is how we would get the percent right there. So the output on the page 16 indicates there are 84 students that didn't go to church at least once a month, have laid out of Facebook friends. Of the 84, how many of them were blank, 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 blank? So it's talking about, and let's go look. It's talking about this leaf right here. Oh gosh, that's impossible to read. It's talking about this leaf right here. So I'm at leaf 2, and so all we need to do is go to leaf 2, and leaf 2 is right here. So let's erase our output on what we highlighted, because we're not going to use that for this answer. The answers to this question are going to be 33, 6, and 45. 33, 6, and 45. Does it do them in that order? I think it does. 33, 6, and is it 45? So 33, 6, and 45, and we've done it. Great stuff there. Which of the following is most likely to be conservative? Circle the best answer. Okay, so this is where we need to look at the other output. Let's look up here at this and see which leaf. So just tell me right now which leaf is more likely to be conservative. So which leaf right here in this output, look at this right here, which leaf is more likely to be conservative? Leaf 1, leaf 2, leaf 3, or leaf 4? So which leaf is most likely to be conservative? Leaf 1, leaf 2, leaf 3, or leaf 4? Which one is more likely to be conservative? Which leaf out of all of these has the highest probability of being conservative? So which leaf out of leaf 1, leaf 2, leaf 3, or leaf 4? So we want to look here. Let's remove the highlighting for the moment. We want to look here at the leaves and figure out which one is most likely to be conservative. Leaf 3, or exactly right. So with leaf 3 being the most likely to be conservative, they have the highest probability. So let's look at their X characteristics. They go to church at least once a month and they do not smoke. So the characteristics of these individuals right here are they go to church at least once a month and they do not smoke. Great job, everybody, right there. Don't worry, this is the practice. We're throwing out some 50 points for positivity right here. So they go to church at least once a month, yes, and they are not a smoker. So when we asked them, do you go to church at least once a month? They said yes. We said, are you a smoker? And they said no. So churchgoers, non-smokers. They go to church at least once a month. Nothing about Facebook friends. They go to church at least once a month, and they don't smoke. So this one right here, they go to church at least once a month, and they do not smoke. So does that make sense right there? They go to church at least once a month, and they do not smoke, which goes along with the X variables we've highlighted right here for the characteristics of the people most likely to be more conservative. For the last one, we need to look at the R-squared. The R-squared for this tree is the percent of variation in Y explained by the variation in X. There's the R-squared. It's 0.099. And when you look at this, what must R-squared do as we split the tree more and more and more? If you split the tree more and more and more, R-squared must do this. And I think this is a great review of decision trees we're doing right here. So if you want a review of decision trees, this has been a really good review. Like, I know what's on the test, and this covers a lot of what's on the test so far. So R-squared must do what? Currently, R-squared is at, like right here at this point, very hard to see, is at 0.099. So it gets bigger. R-squared increases as we put more x's in the tree because x's explain. The more x's we put in, the more we explain. So this eliminates some answers right away. And there are technical possible answers on here. So the answers that are eliminated just by virtue of they cannot happen are these. Now, the most likely, does it say most likely? It does say most likely. That's where I'm okay with this question because this is the most likely. It's unlikely you would see jumps like this. This is a super, those jumps are unlikely, and this is like, no way. Like, that just is not occurring. I've never seen a tree jump that much. Frankly, it might be impossible because it would have to do it via one split. I think some of those are actually just literally impossible. Yep. So the most likely is probably a small increase to R-squared. So frankly, if I were to rewrite these questions nowadays, I'd probably put A, B, C, D, and then it'd be like 0.07, 0.08, 0.09, and 0.10. I could say which of these is most likely. So which of these would be most likely with a current R-squared? See if you can do this one. The R-squared is currently, I would rewrite this question this way if I were to rewrite it today. That's the current R-squared. What's the answer here? A, B, C, or D to this new question. And you are right. So with this new question here, the answer... No. Oh, yeah. There we go. It has to be D because the only thing it can do is increase. R-squared can't go down. So I also kind of like this because a lot of times people think it's a middle answer. I know I'm not trying to trick people, but if you know r squared can't go down, then you're like, well, the only answer it can be is d. And then that also gives you more assurance because you're like, it can only be d because r squared can only go up, which is what you need to know as you split the tree, r squared goes up. And that's the key concept we're trying to reinforce with this question. So I thought you're going to change r squared. I mean, I could have, yeah. If I change r squared, the problem is if r squared right now, it could be a really bad question if this would not be a good question right here. Like this, I don't know. That would not be a good question. Now the possible answers are this, and that would not be a good question. That would not be good. What questions are there? Class in 34 minutes. The instructor's emailed back yet. Let's see. Up. Here we go. Someone said something. Wait, what? I didn't reply to this email yet. Okay. So many things happening in the world. Kim was like, I have class to do in 30 minutes. Yep. It's no, I try to, I'm always trying to like keep up with emails and everything. And so it is open time to ask questions right now. If you have a question, let me know. So what questions are there? What questions are there? What questions are there? It is open question time. Did someone say, did we have one previously? So we had randomness. We could do randomness. What questions are there? I'm going to try to give as much help as I can today, Campbell. So in class today, can we go over the, central limit theorem? Of course. Thank you, Campbell, for being here. It's like, if you notice, I think a lot of people are just like really studying really hard right now. So this is your turn to ask questions. I've had some office hours like no one shows up and I'm just like talking to myself. Could you go over a random problem of randomness that we could see on test? Sure, Molly, let's do that next. You got it. Thank you, Molly. We will do a randomness problem next. And so let's do central limit theorem. So two key concepts as the sample size increases. So the central limit theorem states as the sample size increases, do the three conditions have to be passed in order? There's no real order to them. They are random, 10%, success, failure. They need to all pass, but there's no real order to them. I just like to do random 10% because those stay consistent. And make sure you know that confidence intervals and sampling distributions have the same three conditions. So confidence intervals and sampling distributions have the same conditions of random 10%. And success failure for confidence intervals for the proportion, which is categorical data. So big stuff right there, Paige. They have the same three conditions, and the third, which is the same for them, is because it's categorical for proportions. So the distribution becomes more normal, and the distribution becomes tighter. Probably the most important part of this is the idea of it becoming normal. So with this office hours, this is posted right after Spencer. You can even rewind and pause live. That's one of the great things about being on YouTube here. So this is posted right after. You can check it out anytime. So you can go back and review anything we do. So the central limit theorem says that this curve will become more normal. What happens is if you have too small of a sample size, you do not pass the success failure condition. And here I'll actually show you a graphic of this. Let's talk about when you do not pass the success failure condition. Binomial distribution. So we're going to look at an instance where we do not pass the success failure condition. And so let's take a look over here. And awesome. With this distribution as it is, how many successes would you expect to have? So in this, how many successes would you expect to have right here? If you notice, we have P is equal to 1% and N is equal to 100. How many successes would you expect? The answer is down in the bottom of the page. So we do not meet the success failure condition right here, because we're going to say we're sampling 100 observations with 1% probability of success. So, and if you notice, it's not normal. So we don't meet the central limit theorem, and we don't meet, it's not normal. So with this, we don't meet the normality. Does that make sense? How many successes are we supposed to have? We're supposed to have 10 successes. Now, what happens as we start to have more successes? As we start to have more successes, the distribution starts to become more and more what? Does everyone notice what's happening to it? With more successes, the distribution is becoming more and more what? It's almost like the central limit theorem says, if we meet the conditions, the distribution will be normal. You see, now we're getting towards 3 successes. It's not quite normal yet. Some people will do 5 successes. We do 10. Our condition is 10 successes. We need at least 10 successes and at least 10 failures. It also becomes more and more normal. But what happens with the sample size? If you notice here, the standard deviation of this is 4. It applies to the binomial distribution too. But let's increase the sample size to 200 or 300, and this would be smaller percentage-wise. So ignore that it's not. If we did this as a percentage, like we do it like 7 divided by 300, it's going to be a smaller percentage than 4 out of 100. This is the binomial distribution, a little bit different. Percentage-wise, it's a smaller standard deviation. So it's going to get tighter as we increase the sample size. Oh, it didn't calculate it properly. His applet, I like it, but it runs into problems. Oh, no, it is doing it properly. Okay, good. There's where it breaks. I've broken this applet many times. I don't know why. He needs to fix it. But it will become tighter and more normal. So we do the central limit theorem after the 3 conditions. It's not really the central limit theorem. It just got here. Yeah, we've been doing randomness. We've been doing decision trees. We're about to do more randomness, Amanda. Feel free to ask any questions. We're going to do a randomness example after this. So the central limit theorem says these things if we meet the conditions. Let's put that note right here. Meeting the 3 conditions for sampling distributions and confidence intervals. So if we meet the 3 conditions for sampling distributions and confidence intervals, then we will see as the sample size increases, it becomes more normal. I mean, it's kind of the idea of both of those relate to the sample size, because the standard deviation of this distribution is P times Q over N square root. And look what happens here as N gets bigger. What happens to the standard deviation? Because this is the standard deviation of P hat. What happens to the standard deviation of P hat as N gets bigger? Because we're dividing by N. So if N gets bigger, the standard deviation gets smaller. And that's what the central limit theorem says will happen. That the distribution of these curves will become more normal as we increase the sample size. And we showed, that one's like you have to show it theoretically speaking. And then the other one would be the distribution mathematically will have a smaller standard deviation. And that's just mathematically true that as N increases right here, we will see the standard deviation getting smaller. Does that work right there? Let me take a look. I'm going to take a look at something right here real quick. I want to do a really good, helpful question. Hint, hint, hint. Really good, helpful question. So 2 seconds right here. I'm going to take a look at something and try to do a really good, helpful question. I always like my questions to be as helpful as possible. Where's that at? Here we go. 2 seconds here, everybody. Let me see. Brian's going to make up his own question. This is my own question. Here we go. Okay, good. Okay, this, yeah. Okay, I got it. Let's do a really good question right here. If they meet the conditions, yep. If they meet the conditions, then we know that the central limit theorem is met. The distribution will be normal, and it'll always get tighter. The main thing we care about here is usually the normal, because we're going to use the normal model. So that's meeting the success failure condition for this one. So if we meet the success failure condition for this one, we'll have a different condition later on. But this is for all categorical data. All categorical data has the 3 same conditions of random, 10%, success failure. And success failure means we need at least 10 successes, at least 10 failures. So if we were to look at, Let me double check. I want to double check before I make up this fake question. So, cool. Got it. Okay. So if we were to take a look at this sort of question right here, Brian wants to know if he will win basketball games. Brian is really bad at basketball and plays his brother in 5 games. Let's say 20 games. He has a probability of winning of 10%. In the simulation below, what percent of games does Brian win? Let 00 through 09 represent winning, and 10 through 99 represent losing. Okay. So does everyone see what we have right here? Let's go generate these random numbers. We're actually going to do some randomness right here. So I'm going to go right here and go to numbers. I'm actually going to generate random numbers for this. There we go. There's numbers. Let's go sample. Sample from numbers. I guess I could have just written it there anyways. Replace equals true. And so now we are going to do the following to make it look nice and neat. We're going to sample 20 numbers. Cool. And then let's increase font size. Let's see if we can try to get it so it looks like 5 rows right here. Invalid graphic state. Oh, man. It's new. I'm never going to get it to look perfect. Never. Okay. Well, that's good enough. It's a nice big number so we can see it right here. So we have here a simulation now. We've done it. Awesome. Yeah, Campbell, so glad to hear that, Campbell. We've got some random numbers right here. I'll put in the zeros before this. So this has a 0 right here. This has a 0 right here. Who here can just take a moment, try to figure out via the simulation what percent of games does Brian win? I think the simulation turned out exactly as it would be expected by random chance. But what percent of games does Brian win via this simulation? And so what percent of games does Brian win via this simulation? So here's a really good question. We're going to have to generate random... Nope, not on the exam. You wouldn't have to generate random numbers on the exam. Good question right there, Amanda. We will not have you generate random numbers. Do I win? I think, yep, Paige, you're right, 10% of the games. I'm pretty sure, because I had to put the zeros before them, so that kind of helped me find the ones. Unless I'm misreading, I win 10% of the games, and so we would say 2 divided by 10, or 2... I was like, that's not right. So we'll rerun it here. Great job, Molly. Let's rerun the simulation. Okay. Ooh. How many games does Brian win now in this simulation? So I'm going to ask 2 questions here. Be very careful on the wording because this kind of goes back to the practice test wording. So question 1. What percent of games does Brian win in this simulation? What percent of games does Brian win in this simulation right here? So 0 through 09 represent winning a game. And so question 1, what percent of games does Brian win? And you would look through here, 0%. Now question 2, according to the way the simulation is designed, what percent of time would you expect Brian to win? So according to the way the simulation is designed, so let's put a first question right here. Via the simulation, what percent of games did Brian win? And that would be 0 divided by 20, and that is going to equal to 0%. Brian did not win any games. Now, according to the way the simulation was designed, what percent of games did Brian win? According to the way the simulation is designed, what percent of games did Brian win? Or like, according to the way it's designed, what percent of time would you expect Brian to win? According to the way this is designed. So what we need to look at right here is up top. Let me change colors. Up top, there are 10 numbers right here. There are 90 numbers right here, which makes for a total of 100 numbers with 10 winning numbers. So 10%. And so there'll be 100 numbers. So it'd be 10%. And the way to think about this is the numbers 0 through 99 are basically the same as 1 through 100. You're just taking this 0 right here and bringing it over to the other side. Does that make sense? Like if you were to literally say 1 through 99, that's 99 numbers, and then the 0 is basically the 100, but it's just on the other side to make it 2-digit number combinations. Does that make sense there, Paige? Like I think, just think of 1 through 99, and then you add one more number on it. So 1 through 99, and then you literally have this extra number right here, so that's 100 numbers. I think when you see, it's like, oh, okay, it's just, we're just putting the 100 on the other side, and the reason is we want to make it 2-digit number combinations right there. So the way this is coded, great job right there, Paige, is there going to be 10 winning numbers out of 100. Now, how could we make this simulation better? And what's really great is, this is why I love coding, is because I could do this simulation way better here by just doing the following, and I could run the simulation. You say, Brian, that's way too much for me to figure out. I could just ask percent greater than or less than or equal to 9, and this is going to tell me if they are less than or equal to 9, and then I could get the mean, and we just now simulated 10,000 trials. And that's the law of large numbers right there. So a lot of times simulations can be done a lot easier because I just did 10,000 simulated trials with these random numbers, and you can see it's basically always going to be 10%. We're just doing repeated. I could do 100,000 trials. Oh my gosh, I zoomed out really far. But this is why I like coding. It's like, let's simulate 100,000 trials of this basketball game, and then there's the probability right there, and that's with 100,000 simulations. So I think sometimes, and this is the basics, like learning, understanding how to do a simulation, and then running a simulation like this where you do 100,000 simulations of playing a basketball game with a 10% chance of winning. So all we did right here is see if we got a number less than or equal to 9, which is all we're doing right here when we run the code, is seeing if we get a number less than or equal to 9. I don't want to focus too much on the coding, but as you guys can tell, I love coding. It just helps. It's like, let's just run this simulation 100,000 times, and let's just let the code look at the answer. Because all we're doing is visually inspecting this to see if a number is less than or equal to 9. So why not let the code visually inspect it to see if a number is less than or equal to 9? And then the mean just tells us the percent of time a number is less than or equal to 9. So there it is right there. So what other questions are there? We got 17 minutes before class. We'll probably head off here in like 2 or 3 minutes. Any other last questions? I'm going to try to do as many questions as I can today during class. Whoa, good office hours, everybody. Good office hours. Any other last questions? We'll head off here in a second, but good simulation, really good practice simulation. I think that's got it. Put on a little music. Might go get my second cup of coffee. Go look at some email real quick. And see you in a little bit, Campbell, right? I know, right? You're off back to space. Really good work, really good practice. Keep working hard. You're welcome, Leslie. So we're going to see how the grades go. Test 2 is a little bit lower. It's all right, though. Test 1's like, I think the thing about test 1 is it's got material that, like mean and stuff like that, and histograms and bar charts. And then test 2 gets a little more difficult. Got my fingers crossed. My Pearson's stressing me, too. We're going to see what happens with my Pearson. We're talking, there's not a ton of true false. I'm going to try to, especially during class day, I'm going to try to help with as much as I can. So come to class, check it out. We'll be live in 15 minutes. So swing by. I've sent out the links to all classes, so they have it. But swing by class. I'm going to go get some more coffee, I think. Coffee. All the coffee. With that, I'll be back. 15 minutes. See you live, everybody. Swing by. Bye.